Hey, we're ready to start video lesson 5 on gas pressure. So how does the kinetic molecular theory explain gas pressure? Well, let me tell you. Gas pressure results from the force exerted by a gas per unit surface area of an object. That's the definition. So what do we mean by this? Okay, so let me just show you. Let's say that we have a box. Okay, and in the box we have these particles, gas particles. Well, these gas particles are going to be moving around. And as they move around, they hit the side of the container. That force that they exert on the side of the container, okay, are collisions, and that force that is created by the collisions is gas pressure. So the more collisions you have on the sides of a container, the more force that you're actually going to have as far as the gas pressure. So think about this. If you have no particles present, then you can have no collisions occurring, and so there's no pressure. So an empty space with no particles and no pressure is called a vacuum. And that's pretty much like what we call space. We call space a vacuum because there's no particles. It's just this one big empty space, and there's nowhere, if there are particles, to collide with anything, creating any kind of pressure. Air exerts pressure on the earth. So if we look at, the very thin area between the surface of the earth and the outer stratosphere, that's like a container. And so the air exerts the pressure on the earth. You have all the particles in the air are hitting the surface of the earth and creates pressure. That's what we call the air pressure. So it exerts this pressure on the earth because gravity is holding the particles in the air within the earth's atmosphere. The collisions of the atoms and molecules in the air results in what we call atmospheric pressure. Now, as you climb up a mountain, the density decreases, and as the density decreases, then the atmospheric pressure is decreasing. So why does the density increase? Well, the further away you get from the surface of the earth, the less particles that you have, because gravity is going to be pulling those particles closer to the surface of the earth. So the further away, higher up a mountain you have, it's less dense, you have less atmospheric pressure because there's less particles that are exerting any kind of collisions, with the surface of the earth. A barometer is a device that is used to measure atmospheric pressure. And so we have here a barometer. All right, and so let's say that this is a bowl of mercury. I actually used to make these when I was in 9th grade. Of course, now you can't go anywhere near mercury. But you have an open tube, almost like a graduated cylinder that's upside down. And so what happens, you have the particles in the air, or it's going to exert pressure. They're going to collide with the surface of that mercury. But as it collides with the mercury, it's going to push the mercury up through that open tube. And where the inside pressure is equal with the outside pressure, so you have the barometric pressure and the atmospheric pressure, when they're equal, then that's what the barometric pressure is for the day. It kind of measures how many particles that you have exerting on the surface of the earth. So at sea level, air exerts enough pressure to support a 760 millimeter column of mercury. So you would actually measure 760 millimeters, and that's at sea level. But if you're at the top of Mount Everest, where you're at 9,000 meters high, the air exerts only enough pressure to support 253 millimeters. And why is that? Well, the air becomes less dense, you have less pressure exerted, and so, that's at the higher elevations, you're going to have less pressure. The SI unit, the System Internationale of Units, the SI unit of pressure is called the Pascal. And the Pascal is about 100,000, normal atmospheric pressure is about 100,000 Pascal or 100 kilopascals. We have two older units of pressure that we commonly use, and we use these more so in chemistry than we do in anything else, and that's millimeters of mercury and also atmospheres. That's abbreviated ATM. It's not an atom, but an atmosphere. Millimeters of mercury, because you're actually measuring how high that mercury goes in a mercury barometer. So one standard atmosphere is the pressure that's required to support 760 millimeters of mercury in a mercury barometer at room temperature, or 25 degrees Celsius. So we have a numerical relationship. Take a look at this. Okay, so we have one atmosphere is equal to 760 millimeters of mercury. This is an equality statement. An equality statement way back in the beginning of the school year sets up a conversion factor for us. So we can have one atmosphere over 760 millimeters of mercury. That allows us to convert between atmospheres and millimeters of mercury. Guess what we're going to be doing? Yep, you're right, conversions. And then 760 millimeters of mercury is equal to 101.3 kilopascal. But look at this. One atmosphere would also be equal to 101.3 kilopascal. So these are equality statements we can use to convert between the different types of pressure units. So let's take a look at that. Well, first of all, we have standard temperature and pressure, which is called STP. You might have heard of that abbreviation before. Is defined as a temperature of 0 degrees Celsius at 101.3 kilopascal or 1 atmosphere. So these are numbers that we want to remember. STP, 0 degrees Celsius or 1 atmosphere of pressure. So let's take a look at a conversion problem, converting between units of pressure. We have a pressure gauge and it records a pressure of 450 kilopascal. We want to convert this measurement to first atmospheres, and then we will do that to millimeters of mercury. So let's set up our given, which is the pressure, and that's equal to 450 kilopascal. And I put down what our equality statements are. So 1 atmosphere is equal to 101.3 kilopascal, and 1 atmosphere is equal to 760 millimeters of mercury, since we're going to be converting to each one of those of parts A and B. So our unknowns, first we want to convert the pressure to atmospheres, and second we're going to convert it to millimeters of mercury. So let's set up the problem. We're going to take 450 kilopascals. We're going to use this first equality statement. Our unknown is atmosphere, so we have 1 atmosphere over 101.3 kilopascal. And notice the units divide out, and we get 4.4 atmospheres. And then in the second problem, we're going to start with, again, 450 kilopascal. And we're going to take 760 millimeters of mercury and divide that by 101.3 kilopascal. And we can do that because we know, take a look at this, 1 atmosphere is equal to 101.3 kilopascal, but it's also equal to 760 millimeters of mercury. So these two are equal to one another, and we can use those as a conversion factor. So we have 760 millimeters of mercury over 101.3 kilopascal, and when we divide that out, then we will see that we get 3,400 millimeters of mercury, which equals 3.4 times 10 to the third millimeters of mercury. And with that, that is the end of our video lesson number 5. Be happy, have fun, and dance with me. It's so much fun to dance. This is Mrs. Wheathy, so long for now.